This video has been produced to assist in the effective application of the 12-monthly routines for flooded lead-acid batteries. This battery room is typical of the larger installations you would expect to find in the CBD. The Telepower O&M manual TP00608U firstly recommends container inspection and cleaning. This inspection should also include the safety vents, plates, grid bars, separators, terminals, connections, and finally the electrolyte level. This will determine whether the battery is physically sound and capable of a discharge. Things to look for are blackening of the positive posts from acid migration, which can lead to high resistance intercell connections. Also, corrosion of this area can cause the same problem. Using a torch, verify that the positive plates and grid bars are black and the negative ones are grey. Discoloration, especially of the negative grid bars, will indicate problems which should also show up when voltage and density readings are done. Inspect the cells for signs of tracking, which is caused from dirty batteries and incorrect installations. Cracks in the lid indicate positive post-corrosion. The case-to-lid seal is a very common point where acid can leak from. The separators should be uniform in colour, not bleached from the effects of chlorine. Safety vents should be clean, dry and firmly seated. The sealing washer should not be deteriorated or deformed. The bottom of the stem of the vent should be below the electrolyte level. The electrolyte level should be halfway between the upper and lower marks. The batteries are then cleaned with a cloth moistened with a weak soda solution and then wiped clean and dry. When density readings are taken, it is mandatory to wear eye protection, preferably a full face shield. If using the squeeze bulb type hydrometer, a temperature reading will also need to be noted to determine if density corrections are necessary. When using a digital density meter, the temperature is also displayed. Later models of this meter will also do the density correction for you and thus give the corrected reading. Care should be taken when removing either hydrometers from the vent, as acid drops can be flicked around. These recordings are recorded in the appropriate battery record book pertaining to this battery. The ideal density range should be 1240 plus or minus 5 at 25 degrees centigrade. A wide range in densities indicates that the battery requires a boost equalising charge. When recording the voltage readings, always read the overall battery voltage at its terminals first. This should be 2.2 volts per cell multiplied by the number of cells, and in most cases this is 52.8 volts. This could mean that the voltage at the rectifier may need to be slightly higher to allow for the voltage drop between it and the battery. Cell voltages should ideally be 2.20 volts, but generally the range will be approximately 2.19 to 2.21. This would be the ideal. As the voltage range gets wider, the battery is in need of a boost equalising charge. If the range is 0.05 or greater, a boost charge is a must, or permanent cell damage could result. Any cell floating below 2.17 volts will also require special attention, as it will be sulfated. When all these tests have been done, it can then be determined if the battery is capable of handling a discharge test on the station load. Firstly, ensure that the station load does not exceed the 3-hour rating of the overall battery. Position a voltmeter across the battery terminals to monitor the voltage continuously during the 15-minute discharge test. Check that all batteries are in the float position in the DC cubicle and then turn off all rectifiers. Monitor and record the voltage readings during the discharge so that the results can be plotted on a graph for future reference. If the voltage drops lower than 46 volts, there is a problem in the battery and the rectifiers should be turned back on as the site could be put at risk. Once the voltage has recovered from the initial dip and stabilised, a DC current tong meter can be used to ensure the batteries are sharing the load. Any battery supplying a lot less current than the others will have problems such as a weak cell or a high resistant intercell connector. If all batteries are load sharing, it is fairly sure there are no HR intercell connections, but this should still be checked. The millivolt reading obtained will depend on the size of the intercell connectors, the quality of the joint, and the level of the discharge current. Ensure that there is uniformity in the readings. If an infrared heat detector is available, this can be used to quickly scan all connections, bus bar joints, etc. for overheating during this discharge test. Every joint can be checked from the battery to the DC cubicle. All these joints under float conditions normally do not pass any great currents. So during a discharge test is the time voltage drops can be measured or scanned with a detector. During the last few minutes of the test, quickly read all cell voltages. Do not record these readings as you are only looking for any cell obviously lower than all the rest. For example, 1.91 could be considered as a weak cell. At the end of the 15 minutes, turn on all rectifiers and the float voltage will soon return to normal as only a small capacity has been removed from the battery. This discharge test will produce power alarms such as low float and rectifier fail. Advise the people responsible for these alarms that they will happen and afterwards ensure that they did receive these alarms all the way through to the after-hours centre. At the completion of the test, if individual battery fusing is provided, these should also be checked for alarm extension. When readings such as these are obtained, it is quite obvious that the battery requires a boost charge to equalise voltages and densities. The cells floating low at 2.17 volts would now be sulfated, and it can be noted that these cells are also low in density. Before boost charging the battery, the ventilation system must be checked to ensure its operation and efficiency. The battery to be boosted is identified at the appropriate knife switch in the DC cubicle, which then can be switched to the charge or boost position. Select a rectifier for the boost and switch this rectifier off. Operate its knife switch from float to the off position. Ensure boost control pots are in the minimum position. Switch the rectifier on, switch the boost on-off switch to the on position, and monitor the voltage until the capacitors are fully charged. Operate the knife switch to the charge boost position and then wind up the pots slowly. As most rectifiers are preset to 65 volts on boost, the 20-hour charging rate is not achievable and a current much less will be noted. If this charging current is not successful in bringing up the low cells, an individual cell charger may have to be used. On completion of the boost charge, the voltage and current pots are wound back to minimum and the rectifier is then turned off. The knife switch is operated to the off or middle position. The boost button is turned off. The rectifier is then switched back on and the voltage is monitored until the capacitors have recharged and the voltage has stabilised. When this has happened, the knife switch can then be operated to the normal float position. The battery voltage is monitored until it falls back to or near float voltage. The battery knife switch in the DC cubicle can now be switched from charge straight through to the float position. After at least 12 hours on float, another set of density and voltage readings should be taken to ensure that the boost charge was successful. A general rule is that if a battery is given an annual boost charge, it is unlikely that the voltage and density readings will wander too far from a good equalised range. A few hours of boosting annually could save days of charging, discharging and cell replacements in the long run.